All right, here you see another set of indeterminate powers. So indeterminate forms for limits that you don't quite know what happens to them. And you have to somewhat lift this indetermination to decide what happens to that limit. And it's going to happen. It's going to have a different result for each different limit that you calculate. So the first one is super simple. Everybody knows that this is an indeterminate form, at least everybody. In calculus 1 at this point, we know this is indeterminate. 0 to the power 0, nobody knows for two simple reasons. If you have a to the power 0, that's supposed to be 1 every time, unless a equals 0. And 0 to the power some number, n, like this, is supposed to be 0 every time. So when the base is constant, the base is a constant, not 0, and the power is 0, then you know for sure the answer is going to be 1. When the base is 0 and the exponent, the power is not 0, then you know for sure the answer is going to be 0. You know this for sure because this would be 0 times 0 times 0 a bunch of times, like n times, right? So that will be 0. And this one is just a property of exponents. You can reason through it. But you know for sure that these two are true. But then what happens when both of the bases, when the base and the exponent are both 0? So you don't really know, right? And so you say that this is an indeterminate form. I'm erasing this, and I want to make sure that I discuss with you and tell you that you're not really raising 0 to the power of 0. This is the reason why I use these quotes here. You're not really raising 0 to the power of 0. What you're doing is you're doing something very, very close to 0 and raising to the power of something very, very close to 0. And then you want to see what that equals, right? And so are they going to 0 at the same place, at the same pace? Is this going to 0 faster, right? Or is this going to 0 faster? If the top gets to 0 first, then it's something to the power 0, which is going to be 1. If the bottom gets to 0 first, then it's 0 to the power something, it's going to be 0. So we don't quite know what's going on. And so this is indeterminate, right? I always use quotes. Most of the time I use these to make sure that I remember, that I remind myself that it's not really 0 to the power 0. It's something that's almost 0 to the power something that's almost 0. Another indeterminate power is this one, 1 to the power of infinity. A lot of students, every time that I write this on the board, the number one question that I hear is always, isn't this just 1? Is it 1 to the power of anything equal to 1 every time? Answer is yes, 1 to the power of anything, any number, equals 1 every time. But infinity isn't a number. That's the first observation. And second, you're not really raising 1 to that power. Remember the quotes that I mentioned. This is not really 1 yet. That's some function that's going to 1. So it will be maybe 1.001 to the power of something super large. I don't know, 999, like so. I don't know. So is that going to be super small or super close to 1? Or is that going to be really big? I don't know. If you imagine, if I make it less dramatic a bit, if I do this, multiplying something by 1.01 is like adding or increasing it by 1%, right? If you increase something by 1% and then by 1% and then by 1% by 1% over and over again, 9,999 times, I bet this is going to be kind of large, but I'm not sure. I think so, right? But what about the top? Is it, instead of 1%, this is 0.01%, right? Is that still a big enough of an increase to make it large after 999 iterations? I don't know. So this is also indeterminate, right? The top is not infinity. It's going towards infinity. The bottom, the base, is not 1. It's going towards 1. So you don't quite know whether this is actually 1, whether this is infinity, or something else. And the third one is infinity to the power of 0. And of course, I know what's the most common question or comments students make in response to this, which is, isn't this always 1? Isn't everything to the power of 0 1? And the answer is yes and no. Every number to the power of 0 is 1, right? But infinity is not a number, first of all, right? So raising it to the power of 0 is not supposed to be 1, based on the rules that we know. And second, again, we're not raising it to the power of 0, right? It is not infinity. It's something super, super large. And it's not 0 yet. It's something that's getting close to 0. So is this going to be large or small? I don't know. So these are all indeterminate forms. And I recommend that you spend a little time staring at these. Ask people questions. Play with your calculator. Go ahead and plug in 0.001 to the power of 0.001. What if instead of 0.001, add more zeros to the exponent? See what you get. Add more zeros to the base. See what you get. Maybe this is already too many zeros for most calculators to handle. So you can start with fewer zeros and add more as you see fit. And do the same with these. So play with your calculator. And you can see that these are actually indeterminate. It really depends on how large the exponent is, how small the base is, or how large the base is, depending on which of the 3 types of indetermination. It's very hard to accept that these are indeterminate forms, but once you do, you have to find a way to resolve them. So I'm going to talk about this now. Right, so how do you handle this? Remember, you don't really have 0 to the power of infinity to the power of 0, or 1 to the power of infinity, or infinity to the power of 0. You have one function to the power of another function, and one of the functions, f, is going a certain place, g is going a certain place in terms of limits. So what I do, right, most people do it this way, but I use different notation, is I rename this thing here, I call it y. I'm using this black background for the first time, and I think my markers are affected. See, they're good to see here, but not good to see on the white portion here. So I'll try and use this. So I call this thing y. See that? Call it y. And then, as you can see, I want to know the limit of y, right? So if I call this y, my question is, what's the limit of y? That's what I want to know, right? But this is the indeterminate form. I don't know what it is. So what I do then is I take the natural log of y, and by doing that, I get to bring the power down. You see the g came down as the power. That's a property of logarithms. And then I find the limit of the ln of y. See that? The natural log of y. That will turn into a product indetermination. So now I no longer would have powers. Now I have g times something. So now this is a product. You see that? So I turn a power into a product by applying the logarithm, but that only gives me the limit of the ln of y, the natural log of y. So once I find this, I may need to use L'Hopital's rule here. Let's say this is L. This is telling me that the natural log of y is approximately L, right, for very large or x very close to a. And then I undo this process by raising e to the power of both sides. And e to the power of the left side is just going to be y again. This is one of the properties of logarithms. It's basically the definition of logarithm here. If you need to review logarithms, it's a good idea to do that at this point. But basically, the answer to the problem, again, it's not an equal sign, right? It's approximately equal. The answer to the problem is going to be e to the power of that thing. So I'm going to solve an example. This is just the idea. I'm going to solve an example with you. I've been talking to you about this for 10 minutes. Then go ahead and solve a problem to make sure that it makes sense. Okay. I see this example they want to find. x is going to 0 from the right side. Doesn't matter. Just matters that it's going to 0. I mean, maybe it does. We'll see. But what's going on? Yeah. Okay, if x is going to 0, what's happening to the base? 1 plus, maybe let me use the green one. Actually, no, let me stick to blue. 1 plus sine 4x is going towards 1 plus sine 4 times 0. So it's 1 plus sine 0. So the base is going towards 1. Second, the exponent. This is the cotangent of x. That's going towards the cotangent margin of 0. But what's really going on? Cotangent of x is cosine over sine. And you see here that the sine of 0 is 0. The sine of 0 is 0. This is going to 1 over 0. Right? And because x is going to 0 from the right side, so like I said, doesn't really matter, but it kind of does. This is going towards infinity. Positive. This is always positive. It's 1 divided by something very, very small, but positive. So I use quotes here to represent that this is not really 1 divided by 0, but it's 1 divided by 0.0001 or something, like something very small and positive. So this is going towards infinity, right? So the exponent is going towards infinity. So this is an indeterminate form of type 1 to the power of infinity. And like I said, this is 1 plus something. It's not 1. It's going towards 1. And this is going towards infinity. So maybe if the base gets to 1 first, or if the exponent gets to 1 first, we don't know. This is indeterminate. Okay? All right, now let's see how to handle it. I'm going to do the following. I'm going to say that y is 1 plus the sine 4x cotangent x. I'm going to take the natural log of y, which allows me to, again, I'll take the natural log of this. And then properties of logarithms, I get to bring this power down, this cotangent of x. It all gets to come down. Like so. And I'm planning on using L'Hopital's rule. So I'm going to revert this cotangent and make it a tangent. I'm going to make a quotient show up. Like this. And that's because, as you know, the cotangent of x is 1 over the tangent of x. So that cotangent gets to come down here. If I replace it with 1 over tangent, this becomes 1 over tangent. And then I just multiply the top by natural log and the bottom by 1 here. I end up with this 1 over tangent. Right, so now what's happening to this? As x goes to 0, this is 1 plus the sine of 0, which is 0, and the natural log of 0. So where's this going? This is going towards the natural log of 0. The natural log of 1 divided by the tangent of 0. So this is the natural log of 1 is 0, and the tangent of 0 is 0. So now I was able to, by taking the natural log, to go back to one of the indeterminate forms that I already know about. So I already know about this one. All right, so then what to do here? I can take the limit then of, as x goes to 0 from the right, of the natural log of y. Of this thing. This is, I've already checked, is 0 over 0. So I am allowed to use L'Hopital's rule, which means I take the derivative of the top and of the bottom. When deriving the bottom, I have an easy time. This is just the secant squared of x. And when deriving the top, I have to use the chain rule. This is going to be the natural log of u, right? To call all of this u. And I wonder if I can make this a little thinner. Yeah. Okay. To call all of this u. And so this is the natural log of u. Deriving that will give me 1 over u times u prime. Chain rule like this. So 1 over u will then be times u prime will be sine 4x prime. So again, the bottom stays secant squared. Top will be derivative of 1 plus sine 4x. Got to do another chain rule, but I'll skip it this time. Go a little faster. It's the cosine of 4x times 4. All that still divided by 1 plus the sine of 4x. And now, can I plug in 0? I try again. Can I plug in 0? This is the cosine of 0, which will be 1. 1 plus 0 will be 1 again. And then secant of 0. Secant is 1 over the cosine. The cosine of 0 is 1. So this is just 4. So if you go back screen, the natural log of y has limit 4. So that means that as x gets closer and closer to 0, the natural log of y is approximately 4. So this is the conclusion we've reached. But remember, we don't want this. We wanted y. We wanted this. The given problem was this, the limit of y. So now, to go back from natural log of y to y, I have to raise both powers, both sides to that power, e to the side of, e to the power both sides is what I'm trying to say. If the natural log of y is approximately 4, then e to the power natural log of y is approximately e to the power 4. If thing A equals thing B, e to the power thing A equals e to the power thing B. So the left side is just y, and that means y is approximately e to the power 4. So that is just me thinking. This is, again, kind of BS math, but not really. Because what it tells me is that the limit, the final answer now to close up the reasoning, this is the limit of y. And y, by this sort of BS math, is approaching e to the power 4. So this is e to the power 4. Every time you're going to do the same thing. You're going to start with something that's an indeterminate power. You're going to take the natural log of that power, find the limit of that. That's going to be some number L, and then you're going to raise e to the power of that number L to undo the natural log that we did. So I hope that makes sense. This is just one example. In order to really be good at this, you have to practice, 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 practice. So please do find more problems. Let me know if you need help finding them.